Today we will be starting a new session on the course line commutated and PWM rectifiers. Now let us now go into the three-phase application, and when we go with a three-phase, we can start with the half wave control rectifier, just as we did with a half wave diode rectifier. So what we will do here, now we have these three-phase waveforms which we have plotted here, okay, and when will this, so we can give this name SCR 1, 2 and 3. So when do you think the SCRs will conduct? Okay, so for example, SCR 1 will conduct, okay, whenever this voltage VA, out of the three voltages, there are three voltages VA, VB, VC. Whenever VA voltage is the maximum out of the three, then that is the point when SCR 1 has the natural point of starting, okay, and this natural point of starting is obtained here. You can see here, okay, this is the point here, this is the point, okay. At this point VA becomes the maximum out of VA, VB and VC. So if I can fire the thyristor or SCR 1 at this point of time, it will naturally conduct, okay, because it after that it is the maximum. Similarly VB, okay, the B phase has this as the natural starting point, because from this point onwards B phase is maximum, okay. So SCR 2 can be given gate pulse at this point and SCR 1 can be given gate pulse at this point, okay. So this is the point from where we define what is alpha, okay. So this point here therefore indicates this point here is alpha equal to 0, okay, because that is the point from which the SCR 1 can be easily fired, okay. If you fire the SCR 1, the output voltage will come. So you can see here the V0 voltage, here this voltage comes, this is following VA, and then this will follow VB, okay, and then this will follow VC, okay, and then it will repeat, okay. So this point here, okay, so we have to be careful. So this is the point here, this point, this is the alpha equal to 0, okay, right. So this is how the alpha is defined in the waveforms, okay. So assume again like alpha equal to omega t and 0 less than alpha less than pi. So what is the average output voltage? So here we have shown probably for an alpha equal to maybe 20 degrees, okay, we are showing the average output voltage. But anyway, if you take any value of alpha here, right, so therefore this will be 1 by t, average output voltage is 1 by t. Now what is t here? T equal to 2 pi by 3, right, because the A phase, right, A phase is going to conduct for 120 degrees, right, which is 360 degree by 3, okay. So this is basically 120 degree here, and then B phase will conduct for 120 degree and C phase will conduct for 120 degree. So therefore the time duration for A phase is 2 pi by 3, which is 120 degree, okay. So this is basically 1 by t here, okay. So 3 by 2 pi, so let me just okay, so 3 by 2 pi, and from where to where? So the conduction will happen from pi by 6 plus alpha to 5 pi by 6. As I told you, this point here, this is the pi by 6, okay, where A phase becomes maximum, okay. So the from pi by 6 plus alpha, it will go from pi by 6 plus alpha. So this is the starting point. What is the ending point? Ending point will be how much? Pi by 6 plus alpha plus 2 pi by 3, because each thyristor is going to conduct for 2 pi by 3 or 120 degree. So starting is pi by 6 plus alpha, ending at pi by 6 plus alpha plus 2 pi by 3, which is 5 pi by 6 plus alpha. So this is the ending point and this is the starting point. What is the equation of this waveform? The equation of this waveform, okay, is Vs sine theta d theta. Okay, as you can see here, the red waveform, follow this red waveform. What is the equation? This is Vs sine theta. Okay, theta being equal to omega t. Right? So therefore, V out will become equal to this value. Again, we understand that we can change the output voltage. One thing that you should observe here is this current, okay, these three currents. And if we have a constant current load I0, which is present here, we can say that this current is kind of like quasi square wave. Okay, this quasi square wave current will go into the source. So this is the IA current, IB current, and IC current here. This is this is the grid. Okay, and I have told you previously also, in case of diode bridge rectifiers, this quasi square wave current which is drawn from the grid, this is very problematic for the grid. Grid does not like this. This is one of the biggest problem of thyristor rectifiers. We'll come to this. Okay, again, half wave 3-phase control rectifier is usually not used, and we have to use full bridge configuration. Okay, and the analysis will proceed exactly like a 3-phase diode bridge rectifiers, exactly like this, and we can assume this to be a constant current load. Okay, and we can just quickly recall what happens in a 3-phase diode bridge rectifier. We thought of like this is one pair of 3 half-wave rectifiers. This is another pair of 3 half-wave rectifiers. Okay, and these 3 will conduct based on the, these 3 will cover the maximum envelope. It will trace the maximum envelope of these ones. On the other hand, the lowered diode pair, this pair will trace the minimum envelope. Okay, we have covered this in probably lecture 2 or lecture 3, somewhere there. Okay, and when you add these two up, we get what is the voltage appearing across the output, which is typically this 6 lobe, or we call the 6 we call the 6 pulse rectifier. Okay, there are 6 lobes in the output voltage, and of course you can see here that how the 6 pairs of diodes conduct. Suppose here 1 and 5 is conducting, here 1 and 4 is conducting, 2 and 4, 2 and 6, like this. Okay, so the pairing of the diodes, they are conducting and they are naturally commutating from one to another. So a similar thing will happen in case of the thyristor bridge rectifier. Okay, and we can actually so here then the diodes will get replaced by SCRs. Okay, and we can actually find out what is the output voltage. We can find out, and here also we have to be careful in understanding where is the alpha equal to 0 point. So we see here that in the line voltages, so carefully note that here we are plotting line voltages, and here this dotted one is the phase voltage. So in the line voltage, okay, in the line voltage, wherever this line voltage becomes the peak maximum, so here VAB voltage is the maximum. Okay, then that is the natural starting point for the thyristor to conduct SCR1 and SCR5. So here VAB is conducting, so we are expecting that the path will be completed through like this. Okay, so this is the point where SCR 1 and 5, this is the starting point for SCR 1 and 5 to conduct. So this is the alpha equal to 0. Of course, you can put any other value of alpha. Okay, you can give the gate pulse to somewhere here also. Okay, so you can actually then change the voltage, then the voltage will somewhat change. Okay, we'll see this one in the next slide. But then the next one, you see SCR 1 and 4. So from A, B, it will go to AC. Okay, so then here it will go to AC, because this voltage here, okay, this voltage will get flipped, and this voltage, the blue one is maximum here. Okay, this part is maximum here. Okay, and therefore 1 and 4, okay, so VAC, this voltage is VAC. Okay, this is the voltage which will come here, and so on. Okay, and so if we plot for different values, okay, of alpha, so at alpha equal to 0, we can see here you have this voltage coming like this. Okay, this is the starting point, alpha equal to 0, so you will get this voltage at the output. Now if you shift, so here you can see this is 1 and 5, 1 and 4, 2 and 4. Now if you shift your firing angle, look how 1 and 5 is shifting. Okay, so 1 and 5 started here, now 1 and 5 is starting here, so you have shifted by 60 degree, alpha equal to 60 degree. Okay, now you see where 1 and 5, so alpha equal to 120 degree. So from this point you have now shifted to 120 degree. Okay, so this is 120 degree. You can also shift from here to 1.5 is here, so this is 150 degree, and of course 180 degree. From this point, okay, like this. So what happens here is that when you fire these pairs differently, so when it is alpha equal to 60 degree, what happens, so when it is alpha equal to 0 degree, you were getting this voltage. When you have an alpha equal to 60 degree, what happened, you have shifted 1, and so 1 and 5 is conducting here, so which means that this part, okay, this part, this part of the waveform will now come here. Okay, this part of the waveform will now come here. Okay, and it will be same for all the phases, all the other phases. So this part is coming to here. Okay, when you have alpha equal to 120 degree, then you have this the next part, and you can follow this one by one. Okay, the next part comes in, and so you get this part of the waveform. This is the AB voltage, VAB. So we are basically we are getting parts of the waveforms from different starting and ending points, and as if like those parts of the waveforms are coming at the output. Okay, and because this original AC waveform coming from the supply has both positive and negative parts, so if we take piecewise sections of this waveform and put it at the output, sometimes we may get positive voltage, sometimes we may get negative voltage, as it can be seen. So this is the V0 voltages. V0 voltages you can see. Sometimes they are all positive, sometimes you will see partly positive, partly negative, sometimes fully negative. Okay, and so therefore this output voltage here is fully controllable. Okay, you can change the average output voltage, okay, going from full positive to full negative. Okay, average output voltage can be fully controlled. You can I'm not going into each and every conduction of the thyristors here. You can recall from a first course on power electronics. What is the average output voltage? The average output voltage in this case, again, from where this is my alpha again, so I am going to integrate from pi by 6 plus alpha, because so this is a repetitive waveform. You can see this is a repetitive waveform, and what is the period of repetition is t by 6. Okay, 2 pi by 6 here. Okay, so we are going to start, so this is the pi by 6, so pi by 6 plus alpha, so the starting point is pi by 6 plus alpha, and the ending point is pi by 6 plus pi by 3. Pi by 3 is the duration, because each lobe is 60 degree, right, which means pi by 3. So therefore pi by 6 plus pi by 3 plus alpha, which comes out to be this value, pi by 2 plus alpha. Okay, what is the equation of this waveform? The equation of this waveform, this you should note, because we are going to integrate on this waveform. Okay, the equation of this waveform is the line voltage. It is not the phase voltage. We are going to, so we have found the upper and lower limits of the integration, which is pi by 6 plus alpha to pi by 2 plus alpha. But on which waveform we are integrating? We are integrating on the line voltage. And what is the equation of the line voltage? Root 3 Vs. Vs is the phase voltage, peak of the phase voltage. So root 3 Vs into sine omega t plus pi by 6, because line voltage leads the phase voltage by 30 degree. So this is the waveform. So this waveform has the equation root 3 Vs sine omega t plus pi by 6. So on this waveform we are going to integrate. This is to be carefully noted. And of course d of omega t. When you do this integration, you get this as the output. Okay. So therefore we say that at alpha equal to 0 and alpha we get the, so alpha equal to 0 we get the maximum voltage, at alpha equal to pi we get the minimum voltage, the negative voltage, and of course at alpha equal to pi by 2 we get 0 average output voltage. Fine. चलिए स्टॉप करें क्या थोड़ा सा, और 5 2-3 स्लाइड्स हैं, तो क्या कंटिन्यू करें? Okay, so we will now quickly take an example, okay, in which there is a 6 pulse thyristor converter and it is feeding an RLE load or a DC motor load, as shown in the with say these values E equal to 3000, R equal to 2 and L large enough to consider this as a like a steady current with a ripple free. Okay, the AC input voltage is 4160 volt. This is the voltage and the firing angle is 120 degrees. Determine the power transferred from the AC source to the DC side. Note the polarity of E. So here you see what is the polarity of E. Okay, now when you have a firing angle of 120 degrees, what is the average output voltage? Average output voltage is 3 root 3 Vs by pi into cos alpha. Okay, what is Vs? As I told you, it is the peak of the phase voltage. So 4160 is the line voltage. So 4160 divided by root 3 is the phase voltage into root 2. That gives me the peak of the phase voltage. So this is Vs. So putting it in this value, so we get V0 as minus 2809 volt. Okay, so this is the voltage that is coming here, V0, plus here, minus here. Okay, average output voltage is minus 2809. Now apply KVL on this. So you have a V0 minus I0R plus E equal to 0. Okay, So since there is no ripple on the inductor, so the L di dt is equal to 0. The current has no ripple, so di dt is 0. So therefore we can write this equation V0 minus I0R. Okay, so this is the way the current is flowing. V0 minus I0R plus E is equal to 0. So therefore what is I0? I0 is V0 plus E by R. Okay. And since E is equal to 3000 volt, so since E equal to 3000 volt here, so this is 3000 minus 2809, so 95.5 ampere. This much of current is flowing. Now the third part, determine the power transferred from the AC source to the DC source. Now how much is the power getting transferred from the AC source to the DC side? You can find it out in different ways. One way which I am showing you here is that, so this is the output voltage, okay, this is V0 and this is the current I0. Okay, since the current is entering the plus terminal of V0, so the power which is flowing, so we can assume that the thyristor rectifier is lossless. Okay, so the AC power is equal to the DC power in magnitude. So the power being absorbed by this output voltage, okay, since the power is, so the current is going through the plus terminal of V0, so power is absorbed by this V0 output voltage, or the power is getting absorbed at the output. What is the magnitude of the power? Minus 2809 into 95.5. We have found out in the previous slide the V0 magnitude is minus 2809, so which comes out to be minus 268.3 kilowatt. Okay, now since this power is negative, which means therefore that the output is not absorbing power, actually it is delivering power. So we can say, since this value is here, so we can say that the output is delivering power. Of course, if the output is delivering power and the whole converter is lossless, then the AC source must be absorbing the power. So this is basically a condition in which the load is feeding back power into the AC side. This is a transient condition. This cannot happen indefinitely. Okay, it's a motor load. Okay, if it's a battery, it's a different case. But if it is a motor load, this condition, when the load is feeding back to the AC side, it cannot continue indefinitely, because as soon as the motor loses all its kinetic energy, this phenomenon will stop. Okay, now anyway, so we say that the AC source is absorbing power. Now what is the power dissipated in the resistor? Of course, there is some power getting dissipated in the resistor, which is the I square R, and this is 18.2 kilowatt. How much is the power supplied by the DC source? Okay, what is the magnitude of the power supplied by the DC source? You can see here, for the DC source here, the current is going through the plus terminal, going out of the plus terminal. Okay, when the current goes out of the plus terminal, that source is supplying power. When the current enters the plus terminal, that source is absorbing power. Okay, so the power supplied by the DC source, because it is the current is going out of the plus terminal, the power supplied by the DC source is 286.5 kilowatt. Now note here that the power supplied by the DC source, which is 286, and if you subtract the loss 18.2, and that is the power which is being sent back to the AC side. You can see here 286.5 minus 18.2 will come out to be 268.3. So this is the power which is going back to the AC source. Okay, the AC source is absorbing this much of power from the DC side. Okay, so you have to be careful in how the plus minus conventions are used. Now, so far we have talked about more on the DC side and less on the grid side. Okay, and here we will briefly talk about the problem on the DC side, AC side, on the grid side. What happens with the source current? Okay, what happens with the source means from the grid. How is the grid looking at the whole converter? And as you can see is that if you had seen that when you change the firing angle of the thyristor rectifier, the conduction period of the pair of thyristors remain the same, but their position in the AC cycle, that gets shifted. It goes right. As alpha increases, it goes right and right, like that. So here we have shown you so this gets reflected on the source current as well, drawn from the grid. Okay, and you can see here that as you increase the value of alpha, okay, this is the source voltage which remains the same as before, but if you go on increasing the value of alpha, this current drawn from the source, IS, it gets shifted. It's a quasi-squared waveform, and this quasi-square waveform is actually getting shifted as you change the value of alpha. If you increase the value of alpha, this waveform gets shifted. Okay, what does this mean? There are two things here. So here it is shown the fundamental component of this current. Okay, where is the fundamental component of this current? The fundamental component of the current is here. Okay, so as you shift your firing angle, the angle between the fundamental source current and the fundamental voltage, that angle initially was at alpha equal to 0, this angle was 0. But at alpha equal to 30 degree, okay, so this is the fundamental source current. And this is the fundamental voltage. So as you increase the value of alpha, what is happening? The fundamental source current, okay, that angle between fundamental source current and fundamental voltage, that is changing. In fact, that is getting poorer and poorer. What do you mean by poorer? The angle is increasing. This is the cos phi, the power factor. This is basically the displacement power factor. We have not talked about it, but this is what controls the power factor. Okay, so as you increase the firing angle, actually the rectifier, the power factor is going to get poorer and poorer and poorer. Okay, and this is one of the biggest problems of these rectifiers, thyristor bridge rectifiers, because as you change it gives a great flexibility, because you can change the firing angle and you can get nice variable output voltage. But what happens at the input is something very problematic. At the input side, the converter starts to draw more and more reactive power for the same active power to be dispatched into the load. As you can see here, the angle between fundamental and voltage and fundamental current is increasing. So which means for the same P, you are now going to supply more Q to the converter. Either you think from the power quality, either you think from the active reactive point of view, or you think from the power factor point of view. So you will see here that more and more Q will be drawn by the rectifier. This is one of the biggest drawback. In fact, for large such thyristor based rectifier, we have actually at the input and the AC side of these thyristor rectifiers, we have large passive filters installed for two purposes. One, to supply reactive power to the thyristor rectifier, and the other to improve some of the harmonics being generated. So there are also harmonics being generated. You can understand. This is quasi square wave. The grid does not like quasi square wave current. The grid likes sine wave current. So the source current is quasi square wave, which is a problem. Poor power quality, lot of harmonics, and poor power factor. All these are the problems of thyristor rectifiers. We will take it up as part of week 2, where we will talk more in details about this aspect, from which we will start moving into PWM rectifiers. So thank you for your attention, and here we end our lecture.